6 here. Okay, so I literally just stole this little thing at the top from an actual textbook. So I'm just going to go through with you kind of what it's talking about and then give you some actual examples so hopefully make more sense. So this little box is about what we call complex numbers. Every single number can be written as a complex number, real numbers, and what we're going to introduce today, which are imaginary numbers. So the format for a complex number is kind of in the middle here, and it looks like this: A plus B times I. I is going to be the imaginary part of that. Whatever's in the place of A is what we call the real part, and the B times that I value is the imaginary part. I is not a variable. I'm going to give you a little definition of that in a second, but I is basically invented as an imaginary number to take care of taking the square root of a negative number. That's the purpose of it. All right, so complex number, A plus BI, A and B are real numbers, and you can write a normal number, just like, let's say the number 5. It says if B is 0, then the number A plus BI is a real number. So if I had the number 5, technically I could write it as 5 plus 0i. No one would do that because it's very extra and I don't need the 0i. We would just write the number 5, but you can write that in that format. So any real number can actually be written in this complex format. If we have what we call a purely imaginary number, it doesn't have a real part to it. It says if A in this format is 0 and B is not 0, so B exists, the number A plus BI is what we call a pure imaginary number. So that would look, we wouldn't write the 0 in front probably. We're not going to do that today. So let's say I had 0 plus 3i. We would just write that as 3i, but it can be written in that format. Now, the complex numbers, literally every single number, including imaginary, can be written in this format. So the complex numbers, this little Venn diagram type thing here, real number, kind of like I wrote the 5, falls into the category. You would not have an I with that. Imaginary number here, if it's not purely imaginary, you might have, I'm just going to make something up. Let's say we had 4 plus 8i. That would not be what we would call a purely imaginary number because it has a real part to it, but that would fall into the category of an imaginary number because it does have an I that has a value to it. Pure imaginary number would be what I talked about in this little example right here. Okay, now I'm going to write you a little example with numbers, and then I'm going to show you how they developed I. So, let me make something up. Let's say we have, I don't know. All right, so 7 squared is equal to 49. I'm just going to use a perfect square. All right, so 7 squared is 49. And you guys know kind of if I take the square root of 49, that's equal to 7, right? That's a relationship that we know with a real number. Now, I was invented to take care of a negative under a square root. And it does have a lot of applications in engineering and stuff, so we're just going to do a basic introduction today. But the way this worked, kind of follow this example. So they went and said that I squared is equal to -1. So the reason they made that up is there's no way that I could multiply two real numbers together to get a negative, right? If I multiply -5 times -5, that's positive 25. If I multiply 5 times 5, that's 25. There's no way to multiply two of the same number together to get a negative value, so this is why they developed this. All right, now it's going to follow here the square root of -1 then, by definition, is equal to I. So I'm just kind of trying to relate it there to something you guys already know with real numbers. So this is where this was developed, to take care of a negative under a square root. Now, I'm just going to write it again down here, but that's the relationship. I squared becomes a real number. That's actually equal to -1. This little blank, just so you remember it, I is equal to the square root of -1. So all these questions that we're going to work on today, a couple days ago, you would have told me there's no real solution. Today, these are all going to have imaginary ways that we can break them down. Now, you absolutely do not have to do this, but I'm going to do this in this first question. So we're just going to break down a couple radicals like we've been doing, right? So 121 and it says negative 121. So if you type this in your calculator, it's going to give you an error message. But based on the little definition I just gave you, this is the same thing as negative 1 times 121. Now, by definition, I is the square root of negative 1. So if you have a negative under the square root, what's going to get removed? Because you can always multiply a number by 1 and get it back. So if you need to have any kind of a negative under a square root, you can always remove an I. Does anybody know 121 is a perfect square? Do you guys know square root of 121? 11. All right, the way you would write this then, this is actually what I would call a perfect square in imaginary land. This would just be 11I as your answer. And the thing is, you don't notice, I feel like people get stuck on this when we start working on these questions. I did not put a plus and minus in front of this. I did not introduce the radical into the problem. This square root already existed in the problem. So don't put a plus and minus in front of your answer unless you introduce the square root into the problem, which is going to be usually a situation where you're solving an equation. These do not put a plus and minus symbol in front of any of these problems because there's no equation. We're not solving anything. The radical already exists. Now, for this next one, can 29 be broken down under a square root at all? Like any perfect, no. All right, and you don't have to write this, but you can pull out, because of the negative, an I. It's not considered simplified if you have a negative under the square root. All you have to do is pull out I to take care of the negative. So we would just write this as our answer would be I, and then radical 29 would just stay under the square root. That's all you have to do. It's not considered simplified if it has a negative under the square root. All you got to do is pull out an I. If you have something already existing in front of the radical, which I do here, I have a 3 in front of the square root of negative 100. Now, I would tell you negative 100 is the perfect square in imaginary land. Does anybody know what the square root of a negative 100 would come out as? 10i. Now, you can always multiply. They don't have real and imaginary. You can always multiply them together. All I would do is 3 times 10i. It just works like normal multiplication. This would be simplified to be 30i. That's all it is. If you see a negative under a radical, you're going to have an I in your answer. All right. Now, factor tree away if that is your jam. If not, does anybody know biggest perfect square that'll go into 8? 4. Now, here's what I would do. I would attach the negative to the perfect square. So I'd write that as negative 4 times 2. And then I would say to you, negative 4 is the perfect square in imaginary land. It's just when I take a square root here, square root of 4 is 2, and the negative is just going to bring out an I. So I just bring out a 2i. We would still have a 2 left under the square root, though. So I would write my answer as 2i radical 2. Works just like breaking down a radical. You're just going to have an I with the number out in front. That's literally it. Anybody know biggest perfect square that goes, this is a bigger number, into 108? A little bit bigger than 12 does go in. 36. This is, and I would just attach the negative to the perfect square. If you want to do a factor tree, do a factor tree. Just remember at the end, pull an I out in front with whatever you would put in front of the radical. Now, I would say to you, negative 36 is a perfect square in imaginary land. This would come out as 6i. I have the 3 left under the square root, so I'd write my answer as 6i radical 3. Okay, got one more. This one has a 5 in front of it. So I have 5, and then let's see, 54? I think it's just 9. So I'm just going to write negative 9 times 6 as product that gives me 54, where one of those numbers is a lovely perfect square in imaginary land. So we're just going to remove 3 and an I with it because of the negative. You got the 5 already out in front. So anything that already exists, doesn't matter if it's imaginary, you can always multiply. 5 times 3i would just write as 15i. And then we'd have that 6 would stay stuck under the square root. Can't break that down any farther. Is anybody having a question? Okay. Now, all we're going to do in example 2, I'm just going to have you practice adding and subtracting some lovely imaginary numbers here. And it works just like you would think. So it's going to be combining like terms. We're going to put together, actually, you know what? If you're adding, right? I don't have any numbers in front of these parentheses or anything like that. So you can literally just drop the parentheses. We're just going to combine like terms is how this is going to work. So when I combine my like terms, the real part, so I've got like a 3 and a 4, you just literally add the real numbers together. So 3 and 4 would be 7, and then I'm going to add the imaginary numbers together. So I have 6i and negative 8i. Just, it would be like if I told you to do 6x minus 8x. It works the same way. We're just using the letter I, and it's not a variable because it's technically the square root of negative 1, but this would be minus 2i, and it should be in that format where the real part is first and then anything with an I comes second. So this would be my answer, 7 minus 2i. It's in that a plus bi format. If you have a situation like I have in the second question here, if you are subtracting, you have to be really careful with subtraction. You don't have anything in front of the first set of parentheses that has the 9 plus 10i, so just leave that. The second set of parentheses has a subtraction sign in front. So we have to multiply everybody by negative 1. All right, so this becomes minus 5, but this also, negative times a positive, then turns that into negative 7i. And then you just, same thing as the last question, combine your like terms. So 9 and negative 5, those are the two real numbers. We would just put those guys together. And then I have the 10i and the negative 7i, and I would combine those together. So 9 minus 5 is 4. 10i minus 7i would give me 3i. And I can't go any farther because the 4 is the real part, the 3i is the imaginary part, but that is the format we should put it in. Real part first, part with the I, imaginary part second. Is anybody having a question? Okay, this lovely guy down here at the bottom. Tilt this up just a little bit so I have more room. All right, so I'm just going to drop the parentheses here because we're just adding these together, so that's not going to change any signs or anything like that. What I would tell you here, though, we can simplify both of the radicals that we have in this problem. Does anybody know what you would write as the square root of negative 16? Perfect. So we just change that to 4i. All right, now I have this 8. Now this trips people up, and I really, really don't know why. Don't change this. This is 8 minus, and then what would you write as the square root of negative 25? 5i. So I don't know, sometimes if it's a negative in front of that, people will change that to a positive. Don't do that. Just whatever's in front, we're subtracting the square root of negative 25. Square root of negative 25 is 5i. And then, just like we did in the last question, put the real parts together and the imaginary parts. 2 and 8 would give you 10. And then 4i minus 5i would just be minus 1i. I would probably just write minus I. If you want to put the 1 in front, that's totally fine. And then this last one here, you do have a subtraction. So I have 6 minus the square root of negative 1. I want to distribute this subtraction, which is like distributing a negative 1. So it's going to be minus 11 and then minus square root of negative 64. Anybody know what the square root of negative 1 would be? Ethan, what do you think? Just I. That's the definition, just I. You can put a 1 in front of it if you want to. Then it's minus 11, and again, minus, because we're subtracting here. What's the square root of negative 64 going to be? 8i, perfect. So we're just going to put them together. So you got 6 minus 11, so negative 5, and negative I minus another 8. So it's like negative 1 minus 8, so it should be negative 9i. Is anybody having a question? Okay, the back side of this is where this is going to get a little bit trickier because we're not changing in exponents when we add or subtract, but we're going to multiply on the back. Okay, so I'm just going to put a tiny little reminder here. This is driving me nuts. I'm not doing this right. Okay. Now, at the top, okay, I is the square root of negative 1. That's really more helpful on the questions that we were doing where we were breaking down the radical. The other part of that definition is going to be essential to this example, and that is that I squared, so I times I, if we end up with that, that equals negative 1. It actually becomes a real number. So when you multiply and you get like an x times an x would become x squared, same concept here. If I multiply these, you can always multiply. 3 times 8 would be 24. Then I times I becomes I squared. And then I'm just going to use that definition. I squared is actually -1. It's a real number. So the answer here would become just the plain negative number, -24. It's a real number. You don't have to put plus 0i or anything like that. Just write it. And that sometimes happens when you work with these. The imaginary part might cancel out. That's completely fine. Now, if I do the next question, it's actually really similar to what we just did. It's -5i squared. So what that really means is I'm doing -5i times itself. So -5 times -5 would end up giving you +25, and then just like on the last question, I times I would give you I squared. So this is really 25 times -1, which is then just -25, the real number. The rest of these are going to involve some parentheses. So for this guy, you can always multiply. You cannot always add or subtract. You have to have like terms to add or subtract, but you can always multiply. So I'm going to take I and multiply it by 11. So we would just write 11i. You'd write the I after the number. The other term is I times -10i. So I would just write -10 and then I squared. But we know that I squared is really equal to -1. So this is 11i plus 10. Now, I'm not going to be super picky, but technically to write my answer, I should write the real part first, which would be the 10, and then the 11i is positive, so I'm going to write that second. And so that's a complex number that has two parts to it, right? We've got a real part, the 10, the imaginary part, the 10i, so that's going to be an imaginary number. The last two work like you think they would. It's just two imaginary numbers we're multiplying together. Works like a foil. Or a box if you want to draw yourself a box. I just like to think of it as a double distributive property. So I'm going to take 3 times both guys in the second set of parentheses. So 3 times 2 is 6, and 3 times 4i, you can always multiply, is 12i. Then I'm going to take -7i times both things in that second set of parentheses. So -7i times 2 would be -14i. And the term on the end is going to be the one that's tricky. So -7i times +4i is going to be -28, 4 times 7, and then I times I is I squared. Now, I'm just going to combine these like terms in the middle just as I do this. So I have 6. 12 minus 14 would be -2 for the i's in the middle there. This last term is really -28 times -1. You do not have to write all these steps out if you understand this. -28 times -1 really means that final term would be +28. The only other thing I could do there is add those real parts. I have a 6 and I have a 28, so together that'd be 34, and then minus the imaginary part, which was the 2i. So the real part should come first, the imaginary part should come second. And I've got one more, and then we'll actually apply this to our quadratic equations. Okay, -1 times 5 is -5. -1 times 9i is -9i. Then I have 6i times 5, so I'm going to get 30i, that'll be positive. And then 6i times 9i, I'm going to do 6 times 9, so I'm going to get 54. And then I times I becomes I squared. So I have -5. In the middle there I can combine like terms. -9 plus 30 would give us 21 i's. And on the end here, I really have 54 times I squared means it's 54 times -1. Now, I'm writing out like some extra steps here that maybe you don't need to write out, and that's totally fine. But that last term is really -54. To combine, I have a -5 and a -54. Those are both the real numbers. I can put those guys together, so that'd be -59. And then there's nothing more for me to do with that 21i. But I should write the real part, the -59. Just because it's negative doesn't mean it's not real. So it's got to lead with the real part. That could be a positive or negative number. Here it's negative. And then end with the part that's imaginary that has the I involved in it. Is anybody having a question? Okay, now here's the entire purpose of introducing this. So our whole unit is about solving quadratic equations. In this situation, all these problems, if you would have gotten them a day ago, I would have been like, hey, this doesn't have a solution. Today it's going to have a solution because now you know how to take care of a negative under the square root. Okay, before we get started, do me one tiny favor. Pretend I put a negative with the 7 on that last example. Otherwise, we're not going to have an imaginary answer, and I didn't intend for that today. Each one of these is just a teeny tiny bit different, but I'm going to try to get x squared by itself. So on this first one, I have x squared plus 25 equals 0. So I can get x squared alone by subtracting the 25. And then I'm going to have x squared, sorry, I just messed that up, x squared equals negative 25. Like I said, last week we would have said no real solution, which is true. This does not have a real solution, but it does have imaginary solutions. Here's the part where this becomes important. I am introducing the square root into the problem, right? The square root was not in the original problem. You didn't see a radical anywhere. Now, to solve this, I have to introduce the square root, so that means I have to put that plus and minus symbol, because this question actually has two answers. It is 5i or negative 5i. Both of those would be solutions. You would not see this on a graph. It would not cross the x-axis if we graph the related parabola here, but it does have two imaginary solutions. If you were to plug this back in, which you absolutely don't have to do, but if I were to go in, if I put 5i in place of x, right, we would have 5 squared would be 25, and then I'd have I squared, right, which would be 25 times negative 1. So I had negative 25, and then it'd be plus 25, which would make that add up to 0. You guys do not have to, sorry, I'm off the screen. You guys don't have to plug that back in, but if you do plug that back into the original problem, it does satisfy the equation. So you just have two imaginary answers. We would not visually see that on a graph, but it does have solutions. They just involve an I. This would be my answer. 5i or negative 5i would also work. This guy, I just got to do one step real quick, divide by 2. So I get x squared is negative 48. Now this one's a little bit icky, right, because it's not a perfect square. So I'm going to try and break that down the best I can. Anybody know the biggest perfect square that goes into 48? 16. And I would just, if you got a negative 48 here, just attach the negative with the perfect square. So when you take your square root, negative 16 under a square root would be a perfect square in imaginary land. I'm just going to pull out a 4i. So my answer, we'd have plus or minus 4i radical 3. That plus or minus is just a shorthand way of writing two answers to our question. And you definitely could plug these back in for x if you wanted to go through there and check, and it should work. If you have a question like the next one, don't FOIL, please don't FOIL. If you see some parentheses, you have an equation and it's squared, don't FOIL. What I want to do here, divide by 3, don't distribute either. You can't distribute inside parentheses that have an exponent. So I'd have x minus 5 squared equals negative 9. Now, we're just going to take square root real quick. We introduced the square root into the problem to solve this. So we have to put the plus and minus because there's technically 2 square roots of negative 9. The weird part of this question is you have x minus 5 on the other side that was inside that parentheses. So this guy plus or minus, perfect square in imaginary land is 3i. The other thing I have to do is get x alone, and to do that here I need to add 5. You can't actually add that to the 3i. So the answer would look kind of weird, but it's actually two solutions here. It'd be 5 plus or minus 3i. And I want the 5 in front because that would be like your a, and the 3i would be your bi. So a plus bi, it's two answers here. It'd be 5 plus 3i and also 5 minus 3i. All right, and then I have one more. Pretend I didn't screw that up. Pretend there was like a little negative on the 7. So to start that guy out, what I'm going to do is I'm going to multiply both sides by negative 7. If it's not negative 7, then we're not going to have an imaginary answer, which is the entire point of today. So this would be x plus 8 squared equals negative 14. All right, now square root. So similar to the last question, but also a little bit different. Does 14 break down under a square root? there's no perfect squared that goes into 14. Because of the negative, what I want you to do, just put an I in front of the square root. That takes care of the negative, and then you would just keep 14 underneath. You still have to move the 8, so just real quick, I'm going to do minus 8. And we're going to have x equals, just, I know this is going to look super weird, but this is just what the answer is. Negative 8 plus or minus I square root of 14. You can actually, if you want to, plug this back in for x in the original problem and simplify it if you want to go through it, and it will give you the value equal to 2 if you want to do that in the original problem. Is anybody having a question? Okay, I'm just going to have you do one thing for me on this last example. We're going to spend like a whole day on zeros that are a little bit more complex. So I'm going to get rid of the question in the middle there. So let me relate this back to what we were doing last week. If I give you the zeros, so I'm just going to make up something. Let's say I told you I had a quadratic equation that had zeros at, I don't know, 5 and negative 2. Then you would tell me the two little factors. You would go, oh, okay, x minus 5 and x plus 2. This is kind of what I'm talking about here. So if your zeros are imaginary, works the same way. So if I have 2i, I can write it as x minus 2i, because if I plug 2i in for that, that would set that equal to 0. And negative 2i would look like, in the little factor, x plus 2i. And then technically I should set that equal to 0 if it told me that those were the zeros. Just to relate this so you guys can see. Write this in standard form. So I'm just going to do a FOIL. So we would get x squared. Now this is weird. If you do x times 2i, you would just write it as 2ix. Just write the letters in alphabetical order if they appear, and if you more than one letter in the same term. Now, the imaginary parts will all cancel out here. You won't see an imaginary value in this answer, but if I do negative 2i times that x, I turn around and get negative 2ix, and then these two terms will cancel each other out and go away. On the end, the imaginary part is also going to cancel out. So I'm going to do negative 2 times positive 2, which would be negative 4. And I times I gives me that I squared. So really what I have here is x squared minus 4 times negative 1, which is really x squared plus 4. And that quadratic has the solutions negative 2i and positive 2i. Like if I told you, if I gave you that equation, told you let's solve that, you'd subtract 4, take the square root, plus or minus 2i. Those were the two zeros. That is the quadratic equation that would have those two values as a solution. Is anybody having a question? I'll talk for a real